Our project deals with evaluating infant head kinematics during low-height falls using a finite element approach. In children, traumatic brain injury, a major cause of disability and death, can be a result of accidental falls or abuse. While low-height falls are common among young children, they rarely lead to major injuries, so the possibility of abuse should be investigated when an accidental fall is claimed to cause a major head injury. Multiple efforts have been undertaken to understand the biomechanics of low-height falls in infants, including experiments with anthropomorphic surrogates to understand the forces and accelerations involved in a fall, and computational models to study the infant head during impact. One such computational model focused on predicting skull injury, for example. In this project, we focused specifically on creating a rudimentary model for predicting if brain injury would occur in an infant as a result of a low-height fall.
A two-dimensional model was built in Abacus. We dimensioned our model to that of an 18-month-old. The parts modeled included the brain, simplified as a circle, with the brain surrounded by another circle modeling the cerebral spinal fluid. The skull then surrounded the CSF. All parts of the head were simplified as elastic materials with infant properties from Roth et al. 2006. The neck was also modeled as an elastic material using the elastic modulus implemented by Sullivan et al. In their experimental infant fall study. The neck connected the skull to the body, which was modeled as an oval with a mass of an 18-month-old. After our model was built, we applied boundary and initial conditions. This included a constant gravitational field. The ground was built as a rigid body. The angle of impact was adjusted for different iterations, as well as the drop height, which we simulated by adjusting an applied velocity calculated from the height. We then ran our infant fall simulation.
We are investigating diffuse axonal injury without skull fracture or focal lesion. Therefore, we are looking at strain in the brain. More specifically, we will be interested in particular to strain evaluated at the non-dimensional radius of 0.3, because that region corresponds to the deep white matter of the brain where axons injuries will be sustained. We can observe here the subsequent strain vs time plot for an element situated in the previously mentioned region. We can easily recognize the point of impact where deformation starts. The axon starts to sustain compression then, and as the brain bounces, tensile loads are applied. Playing the simulation, we can see that the cerebrospinal fluid plays a big role in cushioning the impact, sustaining high strains. We compare the influence of height. On the left, you can see with a height of 1 meter, which is approximately the height of a changing table, and on the right, it's 1.5 meters. We found that even though an increasing height increased the strain, it had less impact than we thought, and in particular, it had less impact than the angle of the body. This is surprising because in both cases, the impact is head first and without body cushioning. Those results are to take with a certain care, as our FEM simulation is only 2D and we had to make a lot of assumptions concerning the material properties and the boundary conditions. We would expect our trends to be accurate, but the exact values to be a bit different from reality.
These results suggest great applicability of our research. Say an infant were to be involved in a fall, a physician would then take a detailed history. Reported variables including drop height and angle of fall could be input into our FEM model, allowing much greater specificity than with traditional anthropomorphic models. The simulation would then be used to predict if the reported history could reasonably explain the extent of any injury.